Okay, let's continue. Now here is there is example of of element in this abelian group. It's 1/2, and you can divide 1/2 by 2, for example, in two ways. It's 1/4 and 3/4, and 3/4 multiplied by 2 is 3/2, but 3/2 is the same as the 1/2 in this group. So this is example of two divisions, of two choices of this division, but it exists. So it's of course not unique, but exists. In fact, you have infinite many divisibles here. Okay. Okay. No, sorry, not infinite many, but for maybe a lot of. Okay. Now let's check this proposition, which says that the only abstraction for injectivity is divisibility of elements by integers. Okay. Again, this proposition is based on a general argument with Thorne lemma as maximal ideals. No, let I explain. Okay, proof. Now let I have yes. Let A be injective abelian group. Injective abelian group. I want to prove that it's that A is divisible. No, sorry. Yes, that the fact that all injective groups are divisible, it's kind of easy because I can consider the same injection multiplication by some n, and this map from Z to A unit to any element, and then extension is exactly the division of x by n. So by the existence of this extension, I obtain that x is divisible by n. Okay, maybe not uniquely because I have not uniques of division, not uniques of this extension, but okay. So if A is injective, then of course it's divisible. For any element, for any n, I have such diagram, and extension is division. Okay, it's unit to x n. So the less obvious part is opposite direction. To check that any divisible group is in fact injective abelian group. So let A is divisible, and let I have inclusion of groups, and I have homomorphisms from subgroup. I need to check that I have extension. Thorne's lemma argument. No, it's the same as used for existence of maximal ideals. Says that you have maximal extension. It's a consequence of axiom of choice. I will not check this. The maximal extension from B to some B prime. So I have some maximal extension. I have some subgroup of C which contains B, and I have extension on B prime of my map from B. And this maximal, so it does not contain it's not contained in some greater subgroup with extension. Okay. It's understandable what I mean by maximal extension. Okay. It's some extension, some subgroup, some greater subgroup with extension, and it's maximal with this property. So if I have some greater subgroup with extension, in fact, this subgroup is this group itself. Not any other greater subgroup with extension exists. Why this maximal extension exists? It's homological argument about that. No, you can see what Thorne's lemma means, and Thorne's lemma says that in some mild conditions, maximal elements exist. And in this situation, maximal element exists. No, it's general argument. I will not check this. Okay, but okay. I have some maximal extension. And what I want to check that this maximal extension is in fact C itself. It's what I want. It's what I need. No, okay. Let now assume that it does not coincide with C and obtain contradiction. No, in fact, if I assume that B prime is not C, I just extend it a little more. Okay, but if B prime is not C, and consider some element C from C without B prime. Okay. Consider now так. Да. And then consider the abelian subgroup generated by this element C. Sorry. Consider this element in the quotient. Because C is not in B prime, then its class is not 0 in quotient group. And I consider this subgroup generated by this class in this quotient. Yes, in this quotient. It's not 0 subgroup. It's some cyclic, not 0 subgroup. So it's either Z or Z modulo some integer, okay? It's isomorphic Z or Z modulo some n. Okay, if it's Z, it means that this class has infinite order in quotient group. This means that for any integer k, not 0, kc is not in B prime. Yes, because multiplies of this element of this class is not 0 class. So this element is not in B prime. Okay, it's equivalent to element. It's equivalent to say that k of this class is not 0. No, then, in fact, this means that what if I consider this subgroup generated by element itself in C? No, its intersection with B prime is 0. And then I have direct sum of this and this subgroup in C. And then I have A, and if I have direct sum, then of course I can extend my map. I have considered my already existing map, and consider any value on C. For example, 0 or any other what you want. And this is extension on greater subgroup. This is contradiction with maximality. Okay. And other cases that this subgroup is Z modulo n. This means that NC lies in B prime. No, but n is the minimal such integer. Okay, it's order of this element in quotient. This means that then this means that if you consider, let I denote this existing extension, for example, by phi. I have consider this subgroup B prime plus this subgroup. This is not direct sum because some multiplication of C by n is in B prime. It's not a 0 intersection. No, but it's some sum. It's just some subgroup in C. And I want to define this psi. No, I define psi just in following way. No, psi on B prime is just phi, and psi on C is just phi nc divided by n. nc is in B prime, so phi is defined on nc already. And this is element of A, and I can divide it by n, in any way. Because it's only one element, I choose any division. I choose any division. And define this in this way. And you can check that this rule correctly defines your homomorphism from this subgroup. Sorry. So this is correctly defined homomorphism. Because n is minimal, such integers, blah, 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 and so it's correctly defined. No, and again, this subgroup, it's not direct sum, but it's greater than B prime. Because C is not in B prime. So it's greater. And already, again, I obtain extension. And here I, of course, use divisibility of values of A. Okay. No, and so this maximal extension, it must be C itself, and so in fact I obtain this extension. And so the only abstraction is divisibility of my values. So we have a lot of examples of injective abelian groups. It's Q modulo Z, and for example circle, it's commutative group, and also it's divisible. Okay. In fact, we have following. No, in fact, the following general theorem is true. I will not prove it, but it's called Bioa Criterion. Bioa Criterion. It says that that A over some for some commutative ring R, then module A is R injective. If and only if you need only check this extension property not for all submodules, but only for submodules in R itself. So for ideals, if and only for any ideal in R, if you have map from ideal, then you need to have the extension. If this is true for any ideal, then it's true for any submodules, and this is injective. And this is exactly the situation we consider here, because if you have R is Z, any submodule in Z, any ideal it's NZ, and this extension is exactly the division in your group. So this is we check this criterion for abelian group for Z now. No, and this is true for any commutative ring, in fact. But in general commutative ring, you have a lot of ideals, not only generated by some elements. No, and now some also easy and dual property of injective modules dual to the corresponding properties of projective modules. So, for example, for abelian groups, only projective and injective at the same time is only 0. But over field, any vector space is at the same time projective and injective. Okay. Two exercises. That, for example, direct product of modules is injective if and only if each direct factor is injective. And if you have homomorphism of rings, and if E is R injective, then that is what coextension of scalars is hom R from S to I is S injective. This is important property because from this property you can obtain construct some examples of injective modules. For example, if you consider if you consider some field K and consider some ring homomorphic to some ring or some K algebra, for example. For example, universal and available algebra of Lie algebra. Maybe we will explain it. We will consider it later. and then you have some vector space over K. It's K injective. Now then, for example, such modules you can consider K gamorphisms from R to V, and you can consider it as R module. This is injective R module. It's kind of rich source of examples of injective modules. For example, of enveloping algebras, it's kind of all injective modules of this form. We consider two classes of modules, injective and projective. For these two classes, Hom induced exact sequences from short exact sequences. No, also you can consider the corresponding class of modules such that tensor product with them induce exact sequences. They called flat modules, but maybe we will consider flat modules later, because another easy exercise is that, for example, if M is projective, then tensor product with M, как это называется? Ну, в общем, как это говорится-то обычно? Хорошо, что-то сохраняет. Respects или как? Да, preserves short exact sequences. Sorry, maybe A. So that if you have short exact sequence, then short exact sequence, then the product is also exact. It was an exercise that it's always exact on the right, and the only question is about inductivity of this map, and such modules such that for any injection tensor product with them is injection called flat modules. Okay, maybe we will consider general flat modules later, but now exercise is that if A is projective, then in fact it's flat. It preserves this short exact sequence. It's not equivalent to say projective modules, but it's true. No, it's because it's two steps. It's because it's direct summand of free module, and free module preserves tensor product with free module preserves short exact sequences. Okay, so it's because it's I say this because it's why we do not consider modules with this property now. Especially because we already considered projective modules, and projective modules are good enough for tensor products. Okay, because they preserve this. Injective modules, for example, do not this. So it's projective only. Okay. Now maybe we need to start the homological algebra and say about what we can, how we can replace any module by projective ones or by injective ones. No, the first one. If we have any module, yes, okay. If we have any module, there exists projective module and surjection to M. It's obvious. It's obvious. Why is it obvious?
Again, because it could be a free module. Because of free module.
Yes, because we can use free modules, of course. And it's easy. You can consider some generators of M, or you can consider all elements of M, consider free module. For example, P is direct sum of R summands over all elements of M. And you define this map, define the corresponding 0, 0, 0, 1, 0, 0 on X place to X. It's 0, 0, 0, 0. And this defines you, this is correctly defined the homomorphism from P to M. P is free, so it's projective. And this is of course, surjective. Surjective homomorphism, okay? Okay. What about injective modules? No, so modules projective because we have projection. For any module, we have projection from projective modules. So what about injective modules? What do you think? What we need to have for any module? We have injection to injective module. But this is more much more less obvious than this fact. No, okay, no, maybe no, it's not very hard. So let's check this. Let's construct these injective modules because it's true. So this thing says us that we have a lot of enough injective modules because any module can be embedded to some injective module. So we have enough injective modules, in fact. Proof. We have some module M, it's left R module for some not necessarily commutative ring R. Consider the following thing. IR, it's home of abelian groups from R to Q modulo Z. It's abelian group and it's R module because we have R multiplication from the right on R itself and then it's left R module. In fact, it's just, no, if we consider Z to R, it's F, it's unique ring homomorphism from Z to R, then it's exactly this. Правильно говорю? Да. А нет, вот так. Вот так. Правильно я говорю? Ну да, yes. Ага. Стоп. No, sorry. Сейчас. Фу. Сейчас, нет, неправильно говорю. Нет. Yes. Ага. I consider some abelian group and I consider it's in fact R module. What?
We are proving that there exists a map which injectively embeds M to I, right?
I is injective module.
That's
Of course. Okay. No, here we have projection from projective module. And now we need to injection to injective module. So this is coextension of scalars of abelian group Q modulo Z, okay, by definition. By exercise, that was somewhere here, coextension of scalars preserves injectivity. This is injective abelian group, so this R module is injective. It's left R injective module. It's exercise, but it's not. But it's easy. It was easy exercise. So this is example of injective R modules. Okay, the first step. The second step. We have the following embedding. We can also consider the analogous thing from M to Q modulo Z. But here it's maybe only right R module. We have left R module structure of M, and left R module structure on M gives you a right R module structure on this thing. But then you can consider another one. This is a right R module now, and you consider again, and then this again left R module. And in fact, you have an embedding here of left R modules. No, embedding the map itself is kind of natural. It's M goes to, no, you have some homomorphism, and you need to take some values in Q. No, it's just phi of M. Is it Do you understand what I mean?
Why do we
Definition.
use Q or Z?
Q modulo Z, it's quotient group, it's abelian group.
Yes,
What?
But how did we arrive at this? I understand, but how did we arrive at
No, it's example of injective abelian group, for example.
this?
You may ask why it's not Q, but it's
Yeah.
it's will be right now. It will be right now. Why? It's because we need embedding here. We have this natural map. This natural map is again, of course, it exists for any abelian group here. For any abelian group, you have this evaluation map. It's called evaluation map. You have some element of M, and if you have some home to home, home from home, then some element of M define you homomorphisms from homomorphisms, because if you have homomorphism and element, you can consider its value, the value. And so any element of domain gives you a homomorphism from homomorphisms, okay? Okay, this is understandable formula. This map exists always for any abelian group here. But and now why we need Q modulo Z? No, it's in fact injective model, but now I want to that this evaluation needs to be injective. No, and now here we need that this is Q modulo Z. It's injective and in fact consists only of torsion. No, let's check why this map is injective. Do you believe that this is R module homomorphism? No, okay, it's correctly defined abelian group homomorphism, and in fact it's a homomorphism of R modules. If you don't believe that, please check. It's R module homomorphism. This is left module, this is right module, this is left module, this is left module, this is homomorphism of left modules. Все честно. And only what we need to check that this map is injective. Let's check the injectivity. Okay, injectivity. We have some element M which goes to 0. What does it mean? This means that for any homomorphism, the value of any homomorphism of this element is 0. So what I need to check that for any non-zero element there exists phi from M to Q modulo Z such that phi of M is not 0. And this is here. This is where I need that this is not arbitrary abelian group. It's abelian group of some sort. For example, Q modulo Z, because I need that homomorphism separates my elements. The homomorphism separates my elements in my module. Okay. No, now this is kind of more or less obvious because I need only I consider not R module structure. It's just abelian groups. If I have abelian group, an element of abelian group, I need to define homomorphisms through to Q modulo Z. No, okay, I define my subgroup generated by M. It's some abelian subgroup in M. This subgroup, so because of this is injective abelian group, only what I need to define this map, because then I always have an extension. So I need to define this map. And now is why I cannot use Q, because if it's Z, no, it's infinite cyclic group. Of course, I have map from Z to Q. But if it's not Z, if it's Z modulo N, if it's a finite cyclic group, then if I consider Q here, I cannot define non-zero homomorphism here. But if it's Z or Z modulo N, it's cyclic group, I always can define non-zero, such homomorphisms to Q modulo Z such that f of M is not 0. Okay, it's obvious. If I have Z, N, or Z, I always can define homomorphism to Q modulo Z such that generator goes to non-zero. Because Z and okay. This is why I need not only injectivity but such that it's kind of that I have torsion here in fact. So I can define this map such that f of M is not 0. No, and then I use injectivity, so I can define extension. It's phi. It's my phi. It's some homomorphism from M to QZ such that phi of M is f of M is not 0. So this map is injective. Okay. So I need to injectivity, and I need that I have enough homomorphisms from torsion groups to my group. So I need some torsion here. The simplest example is the injective and torsion group itself. It consists only of torsion. It's Q modulo Z. For example, you can consider S1 here or something like this. It's not important. If you like Lie groups, you can consider S1. It was Pantagin dual. It's a discrete Pantagin dual. Okay. Oh yes, if you know Pantagin duality, it's kind of some relation here, of course. Okay, it was the second step. But this R module is not injective in general. So I only have some injection to some module. This module is injective. This maybe not. But only one step we only need to do. The last step. So yes, consider what. Okay, we have consider this right R module. Right R module. Right R module. And consider surjection from free module, as we considered before. We always can consider surjection from free module. I define it something like this is some direct sum of some index set, okay? Have some surjection. Okay. And now I apply my home to Q modulo Z to this map. I apply home of abelian group to Q modulo Z. This is a general fact that there is not about injectivity here, because for any abelian group we check that surjectivity goes to injectivity. So I obtain injective map of homes. Home abelian group. No, what this is. Home in group M QZ goes to injective map to home my direct sum. Yes, direct sum. QZ. It's injective map of abelian groups, and you can check that in fact this natural map is R module maps. R module map. It's injective as a map of abelian group, but it's also an R module map. It's left R modulus. Yes, map of left R modulus. Okay, but okay, and now it's all. I have injection here, evaluation, injection here, so I have injection here. But this map, by one exercise before, home from direct sum, it's direct product of home AB R QZ modulus of J. And this is injective module. And by another exercise, it's direct product of injective modules, and this is injective. And I obtain injection to injective module. I think this construction shows you that injective module is less obvious than projective. So this injection is less obvious, but it exists. So for example, any abelian group can be embedded to a divisible group by using something like this. No, in fact, any abelian group, oh yes. Okay? 3 steps. 3 steps and 2 exercises, or maybe 3 exercises, something like this. And some checking that all these maps are, in fact, are R module maps. It's okay.
What is that map for surjection from R?
No, some surjection from. We have some left R module and consider any surjection from free module, as you said before. Any, and we use that home always sends surjections to injections. If you consider it's not about injectivity because it's for any models. It sends surjective maps to injective maps. Okay. Cool. We proved that any model can be projected from projective model and can be embedded to injective models. Okay. Now let's start to say something. Let's discuss something about chain complexes. It's basic elements of homological algebra. Let's say something about chain complexes. It's all about what we consider some module things, and now we need to consider some chain complex of modules. But before this, let's discuss chain complexes in general. Chain complexes. Значит, у нас есть, sorry. We have R is our ring, graded ring. We consider left or right, fixed left or right modulus over the fixed ring. For example, left are modules. Okay, what is chain complex? Maybe this you know because you have lectures about homology by Sherigin, maybe, I don't know, something like this. No, not about of R modules. We have not. Yes, it's a sequence of maps of R modules, R module maps, such that composition of any two maps is 0. Yes. I think I will not use these indexes and will just write d squared. It's chain complex. It's definition. Chain complex is a sequence with 0 compositions. Okay. Так. Что по этому поводу мне нужно сказать? If we have two chain complexes, what's the homomorphism of chain complexes or chain map between chain complexes? No, it's sequence of maps such that all squares commute. Yes, all these two compositions coincide. Like something like this, commutative squares. It's chain map. Or morphism of chain complexes, or homomorphism of chain complexes. Chain map. What's the homology of chain complex? No, from this property, we obtain that image of the I is in kernel of the following one, and we can consider quotient module, and quotient module is homology. Ith homology of this chain complex is quotient. No, I think it's familiar definition for some of us. Okay. Any chain map of chain complexes induces homomorphism of homology modules. Yes? If I have chain map, if F is a chain map, then I have induced homomorphism of R. This is R modules. Yes, it's R modules, quotient is R modules, it's R modules. So I have. It's obvious. I don't need to give you a definition of this induced homomorphism. No, the definition is that I have some class of X. X is some cycle. Elements from kernels called cycles. Elements from image calls boundaries. Because D is boundary homomorphism, it's boundary. You have some cycle, element of kernel, and this class and quotient. So then it goes to class of its image. You need only to check that this is correctly defined homomorphism. So if you consider X plus some boundary, the image is also different by some boundary, but it's easy to check. Okay? Okay? It's easy to check. It's easy to check. Or not easy.
I think it's because of linearity of D.
And chain and commutativity. It's because of commutativity. No, okay, let's check. If you have some X plus dy, then effective F is Fx plus F at dy, but F dy is D Fy, so it's boundary. Yes, linearity and commutativity.
Can you clarify here what is di?
What?
What is di?
I don't.
What is di?
Di? No, it's some homomorphism with these properties. It's chain. It's boundary map of chain complex. It's some homomorphism of modules such that composition of two composable homomorphisms is 0, always 0, always 0.
I mean capital D.
Capital D here?
Yes.
It's another chain complex. And I have maps between them, such that all maps compute with boundaries. It's another boundary, boundary D, boundary C. and I have map. And if this map commutes with boundaries, then I obtain a map on homologies. Homologies, that's this quotient modules. Okay. Chain map called quasi-isomorphism. Quasi-isomorphism. No, I will write quasi-isomorphism. If all induced maps are isomorphism of modules. Isomorphism of modules for each number I, for all I. Okay. If chain map of complexes induces isomorphism on all homologies, then we call this chain map is quasi-isomorphism of chain complexes. Okay. Chain homotopy. Да? Значит, if you have again we have chain complex and another chain complex, and you have two maps from one to another one, two chain maps, F and G, for example. Then we say that these two chain maps chain homotopic if there exists chain homotopy. What is chain homotopy? Chain homotopy is map from Ci-1 to Di, and from Ci minus 2 to G minus 1 and so on, S, such that S and then boundary of D no minus or plus, it's not important, in fact, plus boundary on C and then S is equal to F minus G. If it holds, then we say that S is a chain homotopy between F and G. When saying that F and G chain homotopic, maybe no, via this homotopy. Okay. No, first of all, chain homotopy is of maps, of chain maps, is equivalence relation, yes? No, it's easy to check. Okay. It respects addition of chain. Of course, the sum of two. No, of course the set of all chain maps of this chain complex is R module. Is left R module. Oh, sorry, stop. No, sorry. It's a abelian group. It's because it consists of it's a abelian group and yes, and this respects addition on addition on chain maps, because sum of chain maps is also chain map, and if F gamotopic to F prime and G is gamotopic to G prime, then its sum is gamotopic to prime plus G prime. It's this point. No, and also it respects composition. If F, no, and in this notation, composition of Fg gamotopic F prime G prime. If G is map from C to D and F is from D to some U, another chain complex, you can consider composition of chain maps, and then homotopy respects these compositions. Okay. I will.
So what is the notation between del P del C?
A little bit loud.
What does the notation here mean? Delta C, superscript C?
Delta C is boundary on C, and delta D is boundary on D. Boundary of those two chain complexes. So I have DC and then S, and S and then DD. I have two maps from Ci-1 to D-1, and they must be, no, their sum must be the difference between F and G in each in each index. By brackets, I will denote the set of chain maps modulo chain homotopy. It's abelian groups, for example. And you have a correctly defined composition from, if you have this and this, you can correctly define composition of classes of chain homotopy chain maps. It's because of these properties. Why we consider chain homotopies? Because if F and G chain homotopic, then the induced maps on homology coincide. No, it's because of this equation. If dx is 0, it's a cycle, then of this class minus this class is by definition class of fx minus class of gx is by definition class of the difference, and this is s dx plus dsx. This is 0 because of dx is 0, and this is boundary. So the difference is boundary, and class of boundary is by definition of homology is 0 in homology. So this difference is 0. Okay. No, on homology, right here. For example, what is chain homotopy equivalence? If we have chain map, then F is homotopy equivalence, no chain homotopy equivalence, of course. If there exists G of opposite direction, such that composition Fg is homotopic to identity on D, and another composition homotopic to identity on C. And from this property, we obtain that homotopy equivalence and inverse homotopy equivalence induce the opposite isomorphism on homology. Yes. So this we obtain that an inverse isomorphism on homology. So in particular, homotopy equivalence is the example of quasi-isomorphisms, the isomorphism on homologies. It's time to exercise this. Exercise. For example, if you consider, if you station of a field, if you consider R some field, and you consider chain complex of vector spaces of a field, then this is the same thing. Then homotopy, then F is homotopy equivalence if and only if F is quasi-isomorphism. In particular, not in particular, but moreover, you also have that of a field, any chain complex homotopy equivalent to its homologies with zero differential. No, in fact, you can construct quasi-isomorphism, and then from this general fact you obtain this homotopy equivalence. So in fact, of a field, any chain complex is homotopy equivalent to zero chain complex with homology. So no, it's not very much homological algebra of a field. No, it's because all models projective and injective, so we have no homological algebra. So we can see this also in this way. Okay. In general, it's not true, and no, for example, yes, it's not. Yes, and another example. Also, give an example of chain complex of free modules such that it's mapped to zero complexes quasi-isomorphism. This means just that chain complex has all zero homologies. Such chain complex called acyclic. Acyclic, it means that all homologies are zero, and this is equivalent to say that map from zero complex to C or to zero complex are quasi-isomorphisms. If and only but C is not homotopy equivalent to zero complex. So there exists chain complex of free modules such that it's quasi-isomorphic to zero, but not contractible. Contractible means that it's a homotopy equivalent to zero complex. Over field, such does not exist, but over some rings it exists. In fact, it's a very easy example. You can check it. So in general case, even chain complex of free modules, it does not sufficient to say that quasi-isomorphism and homotopy equivalence is the same thing. It's of course not the same thing. No, in fact, maybe I even can give you an example of such complex, and as a hint, it's kind of, you can consider R is Z modulo 4, and consider chain complex Z modulo 4, Z modulo 4, Z modulo 4. It's infinite in both directions, multiplication by 2. It's chain complex, okay? It's example of chain complex. Free modules over Z4 itself. And this chain complex because multiplication by 2 and by 2 is multiplication by 4 is 0 in modulo 4. And you can check that. Сейчас. Почему я? No, yes. And you can check that. What's the homology of this complex? The kernel of multiplication by 2 is Z2. And this is exactly the image of multiplication by 2. No, it's 0, 2. Okay? In yes. Okay? So it's obvious that the homology of this complex is 0 because the kernel of multiplication by 2 is Z2, and it's the image of multiplication by 2. So homology is 0, but you can check that this chain complex is not contractible. There are no homotopy. No, you have only one map to 0 and only one map from 0, and these maps that they are not homotopy equivalences. This map is not homotopic to identity. There are no such homotopy. You cannot construct such homotopy. Okay. Oh yes, I forgot some examples. Some exercises of examples. We discussed that over Z, for example, all projective modules are free. Of course, exercises. Please give me examples of rings in which some projective are not free. Now, for example, one example I give you, if you consider, for example, real numbers, and consider matrices, square matrices of size n by n over real numbers. It's a ring, not commutative, but ring, okay? And if you consider real vector space, then this is module over this ring. Because you can multiply vector by matrix from the left, for example. And this is module over this ring, okay? It's left module. You can multiply vectors by matrices with some, with associativity law and distributive law, and this is example of module, okay? It's left module. Now please check that this module is projective. This module is projective, but of course it's not free, no, because it has smaller R dimension than this module. Of course it's not free, and well, it's obvious it's not free, but it's not, maybe a little bit less obvious that it's projective, in fact. Not free, but not free. And another exercise, okay, you may think that, no, this ring is not commutative. Okay, give me example of R is commutative. And example of P is projective but not free. But not free. In fact, you can consider even R is something like
Polynomials.
what?
Polynomials.
It's very good thing. It's very hard, important, very influential theorem of Serent, Merkuriev, that over a polynomial ring, over a field, for example, any projective model is free. But it's very hard and influential theorem. It was a question of, no, it's related with algebraic theory. It was a question of Serent. It is, sorry. It's Suslin-Serre theorem. Да, Suslin-Serre theorem. So no, it's not polynomials, but in fact here you can consider R something like Z model 6. But okay, if you ask, I can say another bunch of examples of this because there are in fact a lot of commutative rings over which free and projective models are different. Because for example, if you consider differential topology, yes, manifolds, okay. If you consider smooth manifold, and you consider smooth functions, it's commutative ring. And what is projective, finitely generated C infinity M module? In fact, it's the same thing. It's equivalence of categories. It's the same as vector bundle. Vector bundle over M, smooth vector bundle. Equivalence, if you have some bundle, the module is the module of sections of this bundle. If you have some bundle, you can consider its sections, and this is if you have any section, you can multiply it by function and obtain also a section. So section is in fact its module, and you can consider that this module is projective. And on the other direction, any projective model has this form, has isomorphic to module of sections of some vector bundle. And in this bijection, what bundles correspond to free modules? Trivial bundles. So free modules is trivial bundle. So in fact, any non-trivial bundle gives you an example of free but not projective module. Projective but not free module. But it's not obvious. This is a little bit more obvious. Okay. It says Serre-Swan theorem. What I said before, it's Suslin theorem. That if you have field and polynomial, then any projective over polynomials is free. So it's kind of algebraic functions on affine space, and this means that over affine space, any algebraic vector bundle is trivial one. Not because you can say that, for example, over contractible manifold or over, so for example, over Rn, any smooth vector bundle is trivial. But algebraic situation is much more complicated. So to say that over affine space any algebraic vector bundle is trivial is not obvious. It was very famous theorem. But this is true. For example, for polynomial space, polynomial rings, any projective is free. But it's much less obvious than even this theorem. This theorem is not very hard. Okay, but you can consider something like this example. But in fact, if you consider okay, yes, it was examples, yes, and you can consider example of chain complex of free modules such that it's not contractible but quasi-isomorphic to 0. Okay, maybe on the next lecture we maybe check that if you have chain complex of projective modules such that bounded from below, then for such, maybe I can give you this. Okay, maybe I give you as next test today. Okay, let's see what we can do with chain complexes. If we have two chain complexes, this is chain complex of right are modules, and this is chain complex of left are modules. No, maybe you always know what I want to do. I want to consider their tensor product. So I want left and right structures. I can define tensor product. It's chain complex. What is its ith module? No, it's direct sum of all tensor products j dk such that j plus k is I, of course. And I need to define differential. No, I need to define differential only on direct sums because after this I can extend by linearity. So I need to define differential on tensors, on elementary tensors, CD. No, and kind of Leibniz rule, yes? It's D for C differential. So this is C tensor D, dC on C tensor D, plus, and now, no, I think you know what Leibniz rule is, yes? Cauchy sign and something like this, yes? I have differential of degree -1, C of some degree. So C is from Cj, D from I minus j, but it's not important here. -1 I. It's dimension of, oh, sorry, j. Okay, no, please check if it's not obvious that this is differential. So its squared is 0. Okay. And also I can consider maybe even more interesting chain complex of homomorphisms of chain maps, of shifted chain maps. If I have two chain complexes of left, no, or right, or for example left are modules, I can consider this chain complex home differential graded chain. It's I module. Oh, sorry, it's not module, it's abelian group. Yes, this is chain complex of abelian groups, of course, if R is not commutative. If R is commutative, this is a chain complex of R modules, but if R is not commutative, this is a chain complex of abelian groups. This is also, because it consists of homomorphisms. It's set of all, just homomorphisms of CFJ, Cj to G plus or -1. Plus 1. G plus I. Oh. It's set of all, no, it's sequences of R model homomorphisms from Cj to Dj plus I. C0 to Dj, C1 to Dj plus 1, and so on. C minus 1 to Dj to Di minus 1, and so on. It's sequence of homomorphisms of modules. I will not assume that they commute with differentials, not such assumptions. Just sequence of homomorphisms of modules with this shift of indexes. And now I can define homomorphism on homomorphism of such sequence of homomorphisms is sequence of these homomorphisms. I have D F J minus this one I f j minus 1 t c. I is an index of my, is fixed index of my abelian group. I consider Hom from I to Hom I minus 1. This is from Hom dgi to Hom dg I minus 1. So I have sequence of maps with shifted 2 plus I, and I obtain sequence of maps, in fact, with shift I minus 1, because this shift plus I and then differential minus 1. Differential minus 1 and then plus I. This is plus I minus 1, okay? Sequence of 2 shifted from CG to DG plus I minus 1. No, and again, you can check that this is differential. This is differential of chain complex of abelian groups, or R modulus if R is commutative. And one interesting thing, what yes, what is the homology of this differential of this chain complex? What is zero homology of this chain complex? What do you think? No, over any modulus, over any ring, it's not important. No, what is zero abelian group? It's just homomorphism without shift. We consider all sequence of such homomorphisms, we consider kernels, it's some property of such homomorphism, and modular some relations. No, you can check, it's exercise that this is exactly homotopy classes. Property that it's kernel, it's exactly the property that this sequence of maps is chain map. It commutes with differentials, with this differential. And modular relations is exactly modular chain homotopy. So in fact, you can define chain homotopy via some homologies of some another bigger chain complex. It's easy checking. It's directly checking, direct check. If you have chain complexes, we have chain maps between chain complexes. We say that this sequence of chain maps is exact if it's exact in each place. So for each place, this map is exact sequence of modules. Okay? So the exercise and this fundamental fact, fundamental theorem of homological algebra, and that if you have short exact sequence of chain complexes, then you have induced long exact sequence of homologies. So you have I homology of A, you have chain map, you have induced map to I homology of B, you have chain map, you have induced homology to homology of C, and then you have boundary map to I minus 1 homology of A, and etc. What is definition of D? What you have some class of C, some class of C, and C is a cycle in C. Okay. I can C. Okay, maybe it's I and pi. No, pi is surjective. So there exists some B from C is from Ci, from Bi, such that pi of B is C. D pi of B is pi of dB because pi is chain map. This is dC, this is 0. So pi of boundary of B is 0. But no, so boundary of B is in kernel of pi, but kernel of pi is the image of I. So dB is in kernel of pi, is image of I. So there exists some A from I minus 1 because this thing is from b minus I minus 1, such that I of A is dB. No, and this is my definition. D of class C is class of A. It's exercise. You need to check that this is correct. So this class correctly defined by class of C, so it's uniquely defined. This is cycle. This defines class of A. So we need to check the following things: that dA is 0, that class A does not, no, it's does, нет, do, нет, как-то, в общем, depends, ладно, depends only on class C. Also, and D is correctly defined homomorphism of R modules, no, R module, homomorphism, and if we define D in such way, then this exact sequence, this sequence is exact, and sequence in homologies is exact. It's a fundamental fact. No, it's direct check, but no, please, if it's not obvious and if you did not do this before, please do this, okay? It's some direct calculations.
So basically the statement says that short exact sequence
induces the long exact sequence in homology. Yes. Yeah, of course. It's please check correction of definition of boundary map, and that this boundary map gives you a long exact sequence. Understand the definition of D, okay? Okay. Another very useful fact. Why we even care about exact sequences is because we have the following very useful algebraic fact. Also, exercise is 5 lemma. Yes. If I have exact sequence of R modules and I have another sequence of R modules, and I have maps such that all squares commute, then, and if my rows exact, this is F0, F1, F2, F3, F4. Then if F0, F1, F3, F4 isomorphisms, then F2 is also isomorphism. It's very useful algebraic lemma. This is extremely direct checking, so please do this. It's kind of diagram chasing, yes. Okay, let's check this. Maybe I will ask you this on exam, but I will not check this on similar because it's extremely direct checking, and please do that by yourself. It's kind of result which much more better, much better to understand by yourself, by your hands, than see explanation on the board. Okay, it's extremely direct calculation. Please check that if any element goes to 0, then blah blah blah, it's 0, and any element has preimage by this assumption. I think we will not check this on seminars, but please check this. Okay. For example, from this thing we not from example, but cones and cylinders of morphism we will maybe describe on seminars. Okay, maybe we will finish today by the definition of resolution, projective and injective resolution. Okay, maybe now, after some little bit glance on the general chain complex theory, maybe now we are ready to discuss replacement of arbitrary model by projective ones or injective ones. no, we have seen that for any module we have surjection from some projective module. For example, for free module. Now consider. Oh, sorry, no. Yes, you want. Consider. No, it's surjection, but it's maybe it's not isomorphism. Yes, maybe if M is not projective, then it cannot be isomorphism. Then it has some kernel. Yes, kernel K0. Okay. It's also module, and I can consider the surjection from another projective module. And then I define this composition by this map. Then, in this diagram, this sequence is exact in this place, because image of this map is exactly K0, and image of this map is exactly the kernel of this map by definition. So this sequence is exact in this place, okay? By definition. This is surjection, so I have 0 here. So I obtain exact sequence. And I consider this, I can consider this surjection and then kernel, and I can continue this procedure. So I obtain exact sequence. Exact sequence of this form called the projective resolution. If you have module and you include this module to this exact sequence where all these modules are projectives, then this is called the projective resolution of M. Projective resolution of M. Okay? So we now check that any model has a projective resolution. An easy exercise that this projective resolution is the same thing as to say in some other words. You can consider this chain complex with only one non-zero module. It's chain complex because all composable maps are 0. And you can consider some chain complex which has modules only in non-negative numbers, and you can consider chain map. Now, what I want to say that projective resolution of M is the same thing as non-negatively indexed chain complex with non-zero modules only in non-negative numbers of chain complex with pi negative is 0, non-negative is projective, and chain map to this chain complex is a zero number. And this is quasi-isomorphism. So projective resolution is quasi-isomorphism to this model considered as a trivial chain complex by a chain complex of projective modules, non-negatively graded, of projective modules. It's the same thing. No, because this is the same thing. You can easily check that this is the same thing. You can easily check that exactness in this place is the same thing as quasi-isomorphism of these two chain complexes. Okay. So in some sense, we replace module by not one projective module, but by chain complex of projective modules. In such a way which preserves homology. Okay. No, also because we can embed any module to injective one, we can consider injective resolutions. For any module, we can consider inclusion to injective one. So it may be not surjective, so we have surjection to co-kernel of this map, And then this map can be embedded to I1, and this map is also exact in this place. and so on. And so we obtain so-called injective resolution. It's injective resolution. So also the same thing as map from this chain complex to this chain complex. Yes. No. Yes. With zero on the left. This is quasi-isomorphism, and this is injective modulus. Here boundary rises index, and here it goes down in the index. Okay. So we have injective and projective. Okay. No, and the most important property of these resolutions. For example, for projective ones. But we have two modules, and we have resolutions for one of them and for another one. Two projective resolutions. And that we have homomorphism of modules. What then we can do? Yes, we have this composition, and this is surjection, and this is modulus projective. Because of a definition of projective model, if you have surjection and map to the quotient, then we obtain map to the lifting of the map, okay? Such that this diagram is commutative. Okay, what's on the next step? We have that this composition is the same as this composition. So сейчас давайте-ка вот что. Okay. What about this composition? What if we consider this composition and then goes down? This is the same thing as this composition, but this composition is 0. Okay. This composition is 0. So this map composed with this map is 0. This means that this map goes to kernel of this map. Okay. Because then it goes to 0. So in fact we takes values in kernel of this map, but kernel of this map is an image of this map. So in fact, we have map to image of this map, what f, image of f, and we have surjection from q1. And again, we can obtain lift, okay? Because we take values in image, and we have surjection from model to image of the map, because it's to image we always have a surjection, okay? There's only one step here. We have this map. This composition is 0. So this map takes values in kernel, but this kernel is the image because this row is exact. This resolution is exact sequence. So in fact, this composition takes values in image of this map. So if you have this map, we have submodule of image. And we have, in fact, we obtain takes value here, and we have surjection here. And so we have this diagram. We have arrow to image, and we have surjection. And this projectivity, from projectivity, we obtain map from Q1. Okay. No, and all other steps are exactly the same as this step. All other steps are the same at this one step. We have composition 0, kernel, image, and then lift. So we obtain that any homomorphism can be extended to chain map of these resolutions. Now, what exercise that in fact this extension is unique up to homotopy. What this is extension is kind of maybe f hat, I don't know. If f hat and f hat prime two extensions of f on projective resolutions, then they are homotopic. by the same argument from projectivity, you can construct homotopy between them. No, of course, it's because in fact here we only use projectivity of the first one, in fact, and here also. But no, okay, this is exercise. This is important thing. This we will check on seminars, I hope. But from this we obtain what? What we obtain? Okay. If we use projectivity of this one, we obtain this result. And so if you have one module and two resolutions, one and another, and consider identity map, we can extend it to the map in one direction, on another direction. We have two chain maps. This composition is extension of identity to itself. But by uniqueness of the extension, if you have one, if you have only one resolution and identity map, of course you have obvious extension, it's identity extension. And so if you have another one extension, it's homotopy to identity. So this composition is also extension of identity, and so it's homotopic to identity because of the homotopy uniqueness of extension, okay? And in another direction. So these maps are homotopy equivalents, and so we obtain that projective resolution is unique up to homotopy equivalence over M. Okay? No, maybe if it's not obvious, please ask me on seminars on the next study. Как называется? Пара. Как будет пара? Вот урок. Класс. Okay. No, and the same thing also works for injective resolution. Of course, the same thing if you have M, N injective resolutions. You also have extensions, and this extension is unique up to homotopy. And so for one module, we obtain that its injective resolution is unique up to homotopy equivalence. So we obtain that this replacement by projective or injective resolutions is unique up to homotopy. And so if we consider only homologies, then they unique. Okay, I think that is a good place where we stop today.